Hello everyone and welcome back to another video. Today we're solving this integral here, and this is one of those integrals that are very difficult to solve but have at the same time a very simple solution, and there is also a shortcut you can take to get to the solution faster, and we're going to take that shortcut today. But that doesn't mean it's trivial. It's simple, but it's not trivial. We really have to think carefully about each step to draw a conclusion and get the answer. But firstly, there could be a way of solving this integral. So we have a natural log of 1 plus x squared. Well, there is not really, there's really nothing we can do if we look at this integral written in this way. Use up won't work, nothing will work at all. But we could use the Feynman's integration trick to get to the answer by replacing this natural log of x with x to the a and then differentiating it, but we'll do it in another video. Today we're focusing on the shortcut, how to solve this integral here. Now, we have 1 plus x squared in the denominator, and maybe we could do a u sub. Why not? I told you we can't, but let me explain what I'm doing here. So the answer to this integral is 0. It's a very simple number, but it's going to be kind of tricky to get to 0. But maybe we can rewrite this integral in terms of integrals that are 0 but are simpler. What is an example of an integral that is 0 and is simpler? Well, if you take a function that looks like this and you integrate it from a point minus a to a point plus a, the distance from the origin is the same. The two areas are the same because this function is symmetric across the origin here. So if we take this area that has a minus sign and this area with the plus side, it's the same area, but one is reversed. One is under the x-axis, the other is on top of the x-axis. So if we sum the two, we get 0. But here we have an integral from 0 to infinity, so it's a completely different story. Yet we will manage to write it in terms of an integral that looks like this. This is an odd function, an integral of a symmetric interval with 0 in the middle of an odd function. This is our aim, to show that this integral is indeed equal to 0. So without any further clarification about all of this, let's get into the process of solving it. So the first thing I'm doing is to replace do a little u sub. So u equals to the arctangent of, x equals to the arctangent of u. And we all know that the x is going to be the derivative of this with respect to u. It's 1 over 1 plus u squared du. Now, why have I written x and u in this way? Sorry guys, there should be an x here and there should be the u here. So sorry if I just confused the variables, but here is our equation. So we just let u be equal to the arctangent of x and du equals all of this. Now let's do the substitution, and we also have to change the limit of integration. The limits of integration, because here we're going from 0, x equals 0 to x equals infinity. But now we are changing the integral in terms of u. So when the arctangent u of 0, when x equals 0, u of 0, it is the arctangent of 0, and the arctangent is a function that looks like this. and the arctangent of 0 is 0. But as x goes to infinity, let's write it in the following way. As x approaches infinity, we're actually working with limits, but I don't want to write the limit as x goes to infinity because it's annoying. So we're writing it in this way. As x approaches infinity, the arctangent of x really approaches a finite value that is pi over 2. So you should be familiar with this. It approaches pi over 2. And so this equals to pi over 2. Nothing crazy at the moment. This follows because as you approach a 90-degree angle, a pi over 2 angle, the tangent goes to infinity, and this is the inverse function of the tangent. So it's clear. Now, let's get back to the integral. We have u going from 0 to pi over 2 of ln of x, but x is the tangent of u, because we just if u equals the arctangent of x, then of course x equals the tangent of u. This is what we do with inverse function. One is the opposite of the other. So ln natural log of tangent of u. This is tangent of u. Let me put the bracket so it's probably better. Divided by 1 plus x squared dx. But all of this is our du. So we just take in 1 plus x squared dx, and this is what we call du. So we can get rid of the, it's all in here in the du factor. It's not a factor, but you get the idea. And this is now the integral. Notice first that we did something very, 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 very useful. We don't have now an x equals infinity. We have a finite number, and this is going to be, and this turns out to be easy. Well, better, because when we want to represent this integral in terms of a function that looks like this, having finite limits of integration is always better. And now, let's look at this function. Well, can we change the interval? Now we're integrating from 0 to pi over 2, but can we change the variable so that we're integrating over an interval 0 across the x-axis? I mean, an interval with the 0 at its center. So we want to go, if we go a distance a to the left, we want to go also a distance a to the right. In this case, we're integrating from 0 all the way to pi over 2. But can we do a change of variable to just move this interval? We just slide the function across the x-axis. Yes, we can, and we can in the following way. We want to slide this integral. It has the same length. We just want to slide it here so that the center is 0. And to do that, we need the following substitution. So I'm going to write it here. We have a new variable t. Let's call it t. And this new variable is, if we want to move the interval to the left, it means 0 has to go to the negative numbers. So this is going to be u minus the translational factor. Well, it's not a factor, the translational number, pi over 4. Now, let's look at this formula here and learn what this is telling us. if we have u equals to 0, then t of 0, because t is a function of u, of course, equals to 0 minus pi over 4, it's pi over 4. But what if we put u equals to pi over 2? Well, let's find out. T of pi over 2 is pi over 2 minus pi over 4. But pi over 2 minus pi over 4 is pi over 4, because you just multiply these two, and 4 minus, well, 2 minus 1 is 1, so pi over 4, just a simple addition of two fractions. And we have pi over 4. See, now the integral is over a symmetric interval, symmetric, obviously, respect to the y-axis. And this is so nice. So let's rewrite this in terms of the variable u, and I need some space, so I'm going to erase this at the moment, because we've learned that what the limits of integrations are. We just need this formula, and I'm just writing it here, so it's everything more concise. So everything will be more concise. So t equals u minus pi divided by 4. I can get rid of this and also of this line, because we need a lot of space. Okay. Now, let's rewrite this integral. We have, I'm writing it here, the integral from minus pi divided by 4 to pi divided by 4 of the natural log of the tangent of u. But remember, u now equals to we need to bring pi over 4 to the other side, so t plus pi over 4. Let's do the substitution. So tangent of t plus pi divided by 4, and du. Now, what is du? Dt equals du, because we're just moving the function around. The differential doesn't change if you differentiate this expression. You find du equals dt. So let's just change this to a nice du. All right. Now the equation is better, but we still need to prove, well, to find that this integral equals 0, I mean, we need an odd function inside the integral. But the first sign, this is not an odd function, because first we have a natural log, and we know that the natural log is defined only for x greater than 0. And that seems a problem at first. But we have another function inside it, so it's a lot more complicated. And now we need to focus on the inner function. We need to show that this function is odd, because it's really odd. Trust me, it's odd, but we need to show it. How can we show it? Well, we first need to, well, let's just focus on the inner function. I won't bother. I don't bother of rewriting the integral. It's pointless. So let's focus on this function. Well, tangent is sine over cosine. We all know that. So this is the natural log of sine of t plus pi over 4 divided by the cosine of t plus pi over 4. And I just replace tangent of x by sine of x over cosine of x. But we know that we can split the sine and cosine, because we have the sine of the sum of two angles and the cosine of the sum of two angles. And we can use the addition of angles and for just to split sine and cosine in terms of sine and cosine of these angles here. So let's do it. This is natural log. Sine of t plus pi over 4 is sine of t times the cosine of the second angle, so pi over, sorry, it's not a 2, it's a 4, plus the cosine of the first angle, cosine of t, times the sine of the second angle. And we can do the same for cosine. Cosine, the formula is a little bit different, but it's still a formula for the sum of two angles. Cosine of t times the cosine of pi over 4. Now we need to put the minus sign for cosine, because we have a plus here of sine of t times sine of pi divided by 4. Now, cosine of pi over 4 and sine of pi over 4 are square root of 2 are equal to square root of 2 divided by 2, but we don't care at the moment. We just care about the sine of t. What happens if we replace a function is odd, f is odd, if f of x equals to minus f of minus x, and also f of minus x, of course, equals to minus f of x. You just bring the sign to the other side. It means, if we look at this function, that if we stay at x, at this x value, and we find what f of x is, this is the same as minus f of minus x. Minus x is here, this is f of minus x, and you see those two are equal and opposite, so this is minus the other. Very simple. We need to show this. Well, what happens if we replace t by minus t? It just means look at what happens on the other side. Let's see. So we have natural log of, we're replacing t with minus t. Sine of minus t is minus sine of t. And, well, I won't bother about these constants while I'm writing. Okay, I'm writing them so you don't get confused from all of these terms disappearing from the whiteboard. Cosine of minus t is cosine of t, because cosine is an even function, while sine is an odd function. And cosine of t is always cosine of t, cosine of minus t is cosine of t, cosine of pi over 4, minus sine of minus t is plus sine of t, sine of pi over 4. So this is this function with minus t replaced instead of t. And notice something interesting, because if we move this term, we swiped these two terms, and we keep the denominator unchanged, we find that, well, the fraction inside the natural log from here to this function is actually the inverse, because here we have this term in the denominator, here we have this term in the numerator, so it's just kind of exchanged from this to this function. But there is an interesting property of logarithms. Recall that, I'm writing it here because I ran out of space. The natural log of something, let's call this something a, of 1 over a, equals to the minus natural log of a. So if we call all this thing of this expression, or this function inside the natural log a, we have that the natural log of 1 over a, so let's call all of this a, the natural log of 1 over a, sorry, this is, I don't know which is simpler, let's call this is a, because it's the same thing. So we have natural log of a, just getting rid of this equation, but it's absolutely the same. equals to the natural log. Here is the same, but the inverse, so 1 over a. Is this equal? It is not. But we can use the property of logarithms that ln of b equals to minus ln of b equals to ln of 1 over b, because this is b to the minus 1, and you can put the minus 1 in front. So using this, we can say that these are not equal, but these are opposite. This is equal to minus ln of a. So the function inside this function here is an odd function. We're integrating over a symmetric interval, so this integral here equals 0. This is what we've done, and here's how we proved that this integral indeed equals 0. And it's simple. I know it looks messy on the whiteboard now because it took kind of a lot of space, but I mean, it's trivial. Just the important thing is to notice that these two are the inverses of one another, and you can use the properties of logarithms to show that this function is minus this function, but those are the same function evaluated at opposite points. And thanks to that, you can draw this conclusion and say, okay, this integral, this function is odd, so the integral over a symmetric interval must go to 0. And it is indeed 0 because we're summing equal areas with opposite sign. So it's clear that the answer has to be 0. And if you enjoy this video, please subscribe to my channel. I really need your help, and leave a comment below, and also like the video if you enjoyed it. And see you next time with another video. See ya.